My name is Michael Barker. I'm a professor of civil and architectural engineering at the University of Wyoming. And we performed a study on the sustainability of rural steel and concrete bridges. And on this title slide, you see my picture and you see the names and the pictures of the three students that helped me perform this study. And so to start off, let's talk about the objectives of the study. Because sustainability is becoming and will become even a more important aspect for designing bridges as it has in buildings and other infrastructure projects. And so the objectives here were to look at the life cycle sustainability, or perform a life cycle sustainability assessment from cradle to grave of two nearly identical, excuse me, sorry about that. My system's not quite working right. Two nearly identical, functionally equivalent two-lane bridges from Whitman County, Washington. The first bridge was a steel bridge, the Celtis Warner. It was built in 2020. It's 35 foot, 8 inches long. It's a modular steel bridge with 7 rolled beams, corrugated gravel deck, and the county crew built the bridge. The second bridge is a concrete bridge called the Thornton Depot, built in 2019. It's 34 foot long. It is precast pre-stressed beams with 8 beams, which of course make up the concrete deck. And the county crew also built that bridge. And then after the sustainability study of these two bridges, our research looked into procedures for owners or society where they can consider sustainability benefits for the design of bridges. Now, the full report, John almost had it right. The website is shortspansteelbridges.org. And the full report and lots of other information on short span bridges can be found at that website. And so let's take a look at these two bridges. On the left is the Celtis Warner Steel Bridge, and on the right is the concrete Thornton Depot Bridge. And we looked at the superstructure, the construction, the maintenance, and the demolition activities for that life cycle analysis. Now, we looked at only the superstructure so we could compare the two bridges side by side. It was assumed that both bridges would have an expected life of 75 years. Both of the prefabricated bridges and installation equipment and the costs were considered for the criteria that we developed. Now, maintenance was assumed identical for both bridges. This comes from estimates from Whitman County engineers, where there's no maintenance for the first 25 years and then yearly maintenance for 50 years. And then the demolition equipment and the costs are different between the two bridges because of the weight and the size and the volumes of those two bridges. So when we look at a life cycle sustainability assessment, we had to establish benchmarks and criteria. What are we going to measure and how are we going to measure it? And of course, that's going to include greenhouse gases and energy consumption. We're going to consider recycling and the waste stream metrics, and of course, the life cycle costs. And of course, that gives us life cycle bridge results that then we can compare. And then we developed that procedure that considers sustainability benefits for the selection of design of bridges. And this entails monetizing those sustainability benefits and then creating an equivalent cost decision-making process similar to initial costs or life cycle costs that we currently use. So to develop those 4 criteria, or we developed 4 criteria, to develop those, we went to, established systems, the LEED rating system and the Envision credit list that are used on infrastructure projects and building projects. And we looked at those and we said, what of these criteria are important for a rural bridge? And we came up with the 4 of them down on the bottom right, where we're looking at emissions or embodied carbon, energy consumption, recyclability and waste stream management, and of course, life cycle costs. And these are the criteria that we use to compare the two bridges. So under emissions and energy consumption benchmarks, we're looking at the superstructure materials and the fabrication of those materials. We're looking at the construction equipment that it takes to install those bridges, the maintenance equipment during those 50 years of maintenance at the end of the life, and of course the demolition equipment to take it out of service before a new bridge replaces the one that we're studying here. Under recyclability and waste stream management, the benchmarks, the use of recycled materials is important, so the recovery of those during demolition, and of course the material that we have to send to the landfill. Life cycle cost benchmarks, of course, we have the life expectancy of the bridges. Those are both 75 years. And then we look at the costs, the initial costs, the maintenance costs, and the demolition and salvage or landfill costs. And we bring those back to a present value life cycle cost so we can compare those between the two bridges. So to start off, to look at the energy consumption metrics and the emissions, the embodied carbon equivalent emissions, we go to what's called environmental product declarations from the industry, where they do the work and produce the ASTM documents that say, when you collect the resource, manufacture the resource, and fabricate the resource, like a concrete beam or a steel beam, here are the embodied carbons that are associated with that, and here's the energy consumption. And so we searched all of those and we came up with kind of standardized or industry average emissions, kilograms of CO2 equivalent per ton, and energy consumption in megajoules per ton for the different materials that are used in these bridges. For the equipment emissions during construction and during maintenance and during demolition, we did a little bit of work to produce a best estimate of emissions and energy consumption per hour of use of that equipment. And then we divided the equipment up into light equipment and heavy equipment. So now we're ready to look at those bridges. This is the superstructure emissions and energy consumption for just the bridge being put in place, not the construction part of it. And the top is the steel bridge and the bottom is the concrete bridge. And you see on the left side all of the different types of materials or components that are in those bridges, their weights, those metrics for emissions and energy. There is a length factor because the steel bridge is just a little bit shorter than the concrete bridge, or I'm sorry, a little bit longer than the concrete bridge. So for the ones that are dependent on length, there's a length factor. And then we can calculate total emissions and total energy consumed for all of those components of that bridge. And at the bottom in the green, you can see the totals for the steel bridge and the totals for the concrete bridge. Now we have the construction, the maintenance, and the demolition work for the bridges. On the top again is the steel, on the bottom is the concrete bridge. And for construction, estimated, or these are actual hours on site, and then there was a usage factor that was estimated for total emissions and total energy consumed for that. For the maintenance is the same between the two, so those numbers are identical between the two bridges. And then down for demolition, it did take a little bit more time and equipment usage to demolish the concrete bridge, so we see those totals. But now we have, for the life cycle for these two bridges, the emissions and the energy consumption. On the top is the emissions. We see the steel superstructure and construction and maintenance and demolition, and then a total. And for the energy consumption, that's the table at the bottom. And so these are kind of the first results we see. We see that for the superstructure alone, the steel has only 68% the emissions of the concrete bridge. For energy consumption, it's 89%. For construction, it's a little bit less just because it's a lighter bridge and easier to put into place. For maintenance, those two are the same. For demolition, again, the steel is just a little bit less because of the lower volumes, the lower weights, and the work that it takes to demolish the bridge. And then we have the totals where we see for the steel bridge, it's 79% of the concrete for emissions, and it's 92% for the energy consumed. So these are our first results, and the result pretty much is for these two bridges, steel has sustainability advantages. For that recycling or surplus and landfill criteria, steel is 98% recycled, and somebody is willing to pay for that material, and the going rate is about $100 per ton. Now, Whitman County would not plan on recycling this concrete bridge, but in the country, there is a lot of concrete that's recycled for road base and other things. And so it was assumed that 80%, which is about the average, national average of the concrete, is recycled, but they're not willing to pay for you to give them the concrete. You still have to pay a cost of $4.10 per ton. But the landfill costs, if we sent that concrete to the landfill, it costs $75 per ton. So it is a better economic decision to recycle it. So this next table here, shown about in the middle, just shows that for the steel and the concrete bridge, that 98% of the steel is recycled and 80% of the concrete is recycled, and that's how many tons are recycled and how many tons go to the landfill, and then what is somebody willing to pay for the steel that's recycled, and how much does it cost to send material to the landfill. And we get those costs at the bottom two tables, where green is a surplus, somebody paying for the recycling, and kind of orange is the cost for recycling or sending it to the landfill. But now we're ready to look at a present value of cost for the steel bridge on the top and the concrete bridge on the bottom, where the top left table is for the bridge itself, for putting the bridge in place. Then the table right under that is for the maintenance for those 50 years at the end of life. And then on the top right for each bridge is the demolition costs, which include the salvage costs for the steel recycling. And so we can gather all of these costs, get them in present value dollars using a Office of Management and Budget discount rate of 1.7%. And then of course we can see the results. For the life cycle cost, steel is on top, concrete's on the bottom. The superstructure, the total initial, so the superstructure is the prefabricated elements being delivered to the site. The total initial is getting it constructed and in place. And then the present value for the maintenance, the present value for the demolition, and of course the total life cycle cost. And again, here's our second result. Steel bridge has lower initial and life cycle costs. Initial about 80%, total life cycle still about 80%. Now that we have the sustainability data from the two bridges and the life cycle cost data from the two bridges, there is a decision to make. Which bridge should be built if we are trying to make a design decision? And here's where we develop that procedure considering sustainability in the design decision. And we do that by monetizing sustainability benefits. Now, let's go back to what sustainable design is. It is predicated on the idea that society is willing to pay extra money for reducing harmful effects on the environment. Now, for these two bridges, this decision is trivial because, as we saw, the steel has higher sustainability benefits, which means lower carbon emissions and lower energy consumed and more material being recycled. And it has lower life cycle costs. And so this is a trivial decision, no decision required. But what if the steel bridge had cost more than the concrete bridge? Yes, it has sustainability benefits. And what if it had cost more than the concrete bridge? How do we make the decision on which one to build? So considering sustainability in the design of a bridge entails answering the question, what additional costs would society or the owner be willing to pay to increase sustainability benefits? And so we're just going to play a what-if game here. So suppose society is willing to pay 20 cents per kilogram of CO2 equivalent emissions reduced, 4 cents per megajoule of energy reduced, and $50 per ton of landfill reduced. And when we monetize those, then an equivalent cost can be determined for any number of alternatives for a bridge project. Now, the basis for the analysis is the lowest cost alternative. And then from that, you can calculate an equivalent cost for all of the alternatives by taking the initial cost, or you could use life cycle cost, but say initial cost, and then subtracting off the reduced kilograms of CO2 times its 20 cents per kilogram reduced, minus the reduced megajoules of energy consumed times its 4 cents per megajoule, and the reduced landfill, the reduced tons sent to the landfill times its $50 per ton. And then you just do that for all of the alternatives, and then the lowest equivalent cost alternative is chosen considering the sustainability benefits and cost of that alternative. Now, this is actually an incremental benefit cost analysis that is hidden in terms that owners and society can understand. It's similar to an initial or life cycle cost decision-making process. Just look at the lowest equivalent cost, because incremental benefit cost analysis can become confusing. And so this is couched the same as what we do and have done historically. So let's look at the example of that. Here I have 5 alternatives ranging from the lowest initial cost at the top at 100,000, and then 105, 105, 107, 107. And then through the process that we just went through, we can calculate the initial or even life cycle kilograms of CO2 equivalent embodied carbon, megajoules of energy consumed, and the amount sent to the landfill for each of those alternatives. Then using the lowest cost as a base, we can look at, does the next alternative reduce the carbon or the energy or the landfill usage from that base alternative? And we can see alternative 2 does not reduce kilograms of carbon. It actually increases. It does reduce energy, and it does reduce landfill. And then multiply those by those metrics of 20 cents per pound, 4 cents per megajoule, and $50 per ton to get a cost benefit, and then calculate a total cost benefit, and then an equivalent cost. Now, alternative 3 has the lowest equivalent cost at $99,179, which of course is that initial cost of 105 minus the total cost benefit of $5,800. Now, alternative 1 is the lowest cost, but it has a total cost benefit of 0 since it is the basis of this. And if we look at a few of the others, we can see what happens. Alternative 4 has the highest sustainability benefits at $59.56, but it costs $7,000 more. That's an incremental benefit cost less than 1. You're getting a benefit of $59.56, but it costs $7,000. So that's an incremental benefit cost less than 1. The sustainability benefits are not worth the extra cost. Society's not willing to pay $7,000 for what they believe is $59.56 of benefits. Now, alternative 3 did have the lowest equivalent cost. It has $58.21 more sustainability benefits than alternative 1 and only costs $5,000 more. That is an incremental benefit cost ratio greater than 1. The sustainability benefits that society is willing to pay for is $58.21, and they only have to pay $5,000 for it. And that's why that benefit cost ratio is greater than 1. And then alternatives 2 and 4, the additional sustainability benefits, if any, do not outweigh those additional costs. So alternative 3 costs $5,000 more than alternative 1, but it has a societal accepted rate of return of $58.21. So that is the alternative that should be chosen. And this is incremental benefit cost analysis with monetized sustainability benefits. And then the society or the owner can choose what those metrics are. If it's not 20 cents per ton per kilogram of CO2, what is it? Or they can literally ignore something. So it's very flexible. The owner or society determines the acceptable cost for those sustainability benefits. And owners understand equivalent costs. It's comparing costs just similar to initial costs or life cycle costs. So to kind of summarize and conclude, the results for the Celtis Warner Steel Bridge and the Thornton Depot Concrete Bridge are that for the installed bridge, steel has 30% less emissions. Steel had 11% less energy consumed. For the life cycle costs, or for the life cycle assessment, steel had 21% less emissions, which is equivalent to 31,300 equivalent vehicle miles. That's a lot of times that's what they compare it to in sustainability studies. And steel had 8% less energy consumed, which is 0.6 homes for a year. And of course, for cost, steel had 22% less prefabricated bridge costs, 20% less installed initial costs, and steel had 19% less life cycle costs. For the equivalent cost procedure, it's similar to initial cost or life cycle cost decision making. It is owner or society driven with acceptable sustainability benefit costs. And it's flexible in the analysis. You can look at the superstructure only, or the structure and the equipment. You can look at initial costs or life cycle costs. You can look at only the prefabricated bridge, the installed bridge, or the life cycle bridge with or without maintenance and demolition. And you can look at any combinations of emissions or energy consumed or landfill use, or you could add other criteria to that. And you could even consider total energy or only non-renewable energy, but you have an equivalent cost that is the initial minus the benefits gained by reducing harmful effects to the environment. And with that, I would like to acknowledge the American Iron and Steel Institute, Mark Timmons, the VP for Sustainability, and Dan Snyder, the Director for the Short Span Steel Bridge Alliance. Of course, Whitman County Engineers and Assistant County Engineer for all of their help with the estimates and the information on these two bridges. And at the University of Wyoming, we had a little research group that looked at the process and the results, and that was Tony Denzer and Bill Bellamy. And of course, the opinions and conclusions here are from the University of Wyoming and not necessarily the steel industry. So these are the results of these two bridges, which gives us kind of what I believe are the first results looking at the sustainability of bridge structures in the rural setting.